hopefully within this next 2 days, you guys will be able to take away a lot of different things and applications to your particular discipline. I thought I'd put up the schedule in case you guys haven't seen it before, and I'm not sure if you have or not. But we're going to start off with kind of a background in theory, and I won't go too hard into the calculus. So, and then we'll have a demonstration, and then we'll have all afternoon is going to be lab exercise, so you guys get to play. Now, if you guys have any type of images or anything else, or any type of impression evidence that you want to look at, you should create it. In fact, you can create some on paper, or even for question documents, indentations on paper. And we'll show you some of those applications within some of the PowerPoints. The application has really helped in a serial pedophile back in Idaho or something, looking at 10 pages down from the writing and looking at some of the journal of one of these individuals. So it's amazing what you can do with some of this stuff. And anything that has any kind of depression or raising of an impression, I think you have a possibility of looking at more detail than you would have otherwise expected. So we'll do exercises, and hopefully we'll have enough time. And if we don't have enough time to review the exercises down the bottom, don't worry, because we'll do that the next day. And so take the whole afternoon in developing these things. You guys all have thumb drives there, and the way we're going to work it is you're going to just plug that into the laptops that are next to the instruments, and everything will be driven from that, although you have to format the location, right? Or you'll be there.
Yeah, to view the file.
Right.
You have to tell it where to put the images. So you just need to pick the thumb drive when it comes in and tell it to download it to that file folder. I'll go over that in the instructions for the exercise.
Right. And then tomorrow also we'll talk about building your own dome. And then we'll talk about a camera and lens evaluation selection on what are the minimum requirements for looking at high resolution images. And hopefully everybody has kind of a background in digital photography. The megapixel really kind of defines how much you can blow it up before you pixelate. That's all it does. And so we'll discuss that a little bit. And then we'll discuss kind of what you see in PTM versus traditional images. If you've done any type of imaging, taking them from at least 4 different sides of a shoe impression versus what the PTM does for you. We'll discuss that. And then kind of a admissibility in court. Oh, the class is over at 2:30, so whoever was worried about that. Class is over at 2:30. So we'll discuss a little bit about the court aspect. And you'll start to see as we go through the PowerPoint presentation, you'll be able to see the varied academic professions that use this thing. So it isn't just forensics, and it isn't just something that's kind of a willy-nilly kind of black magic thing. And in fact, the mathematics has been around, gosh, probably in the early 1900s. The calculus, I mean, if you guys have taken any type of calculus, trying to figure out the area of a sphere, and if you took a core out of that sphere and calculated that area, that's all. It's the same type of mathematics. It hasn't changed. It isn't anything new. So I don't anticipate that we're going to have a whole lot of problems. Not only that, but each one of the single images that you take. In our particular case, we're taking 64. But I think the minimum is, what, 36 or?
Basically, the minimum was 32 when he initially did it. But he said he went to 50, and it gave much better images. The transitions, as you'll see as we move it around, are a lot smoother. So really, we're recommending a minimum of 50. And we went with 64, and that seems to work pretty well.
Because it's an even number.
Yeah. It divides well.
But so hopefully we can give you sufficient information during this period of time. And for those of you that haven't seen a PTM, I thought I'd give you just a little taste of it in the beginning. The PTM, as it's kind of a merging of multiple different images, and then you kind of use a rollerball type application to roll it around, and this shades the light from any different direction. In a hemisphere, if you think about a hemisphere, and in anything from top to bottom. So as you move towards the center, you get the light coming straight down. Any side is a side angle. And then, because of the mathematics involved, we can do this thing called specular enhancement. And specular enhancement kind of gives you a second derivative. But you can also bring out more different types of images or better detail by doing that in some cases. Especially in things that we found were things like bloody shoe prints and things like that. Because that little raising of it, it seems to bring out some of those things a lot better. So, I mean, that's essentially the PTM. And we'll go through a lot of these images over the next couple of days. So if you missed that one, there'll be plenty of time. Why does it do that? Okay, so we're going to talk about the evaluation and application of this polynomial texture mapping. It is a polynomial simply because in the algebraic equation it's a polynomial formula. And then we'll talk about why it's a texture and a mapping. But the PTM is essentially a very simple idea. It is very similar to anything that you've done with any type of oblique lighting photography and trying to bring out any type of detail, whether or not it's in shoe impressions, in latent prints and question documents, and any of those things where you have impressions. The angle and the distance of the flash to the object brings out more or less detail. And it is what we looked at it for was to bring out more of the photorealism or a better, it's almost a three-dimensional. I won't say it's a three-dimensional image, but it kind of brings out that detail that we're kind of looking for when we're comparing different parts of a shoe or a tire track. So, if you think of a half dome and you cover it with very oblique lighting on the sides and then step up all the way to the top, that's how you get your different images. And then imagine taking all those images and collating them together. And what the mathematics, the polynomial really does is in between two different light sources, it calculates the light value. So that's why over a hemisphere, you have an infinite shading ability, not only between, let's say, light 63 and 64, but any number of steps in between 63 and 64, that light value is calculated based on the mathematics, which is pretty cool because then now not only do you have 64 different angles, now you have an infinite number of angles that you can look at. And one of those angles may be the one you need to look at some type of a unique mark that you're trying to compare. So it's pretty cool. Let's see. What it does is it looks at various types of, let's see, there are, if you think about a digital camera or any type of color photography, there are three different types of values, a red, green, and blue. And combining those will give you the total coloring. But what it does in the PTM is it calculates the value for not only the red luminescence, but the green and the blue luminescence. And when we turn off, turn on different things, we can cut or reduce or increase light to any one of those or all of them. So the total luminescence is a combination of 9 different values within each one of those things. And they're the coefficients of a biquadratic equation, which is this. And that may not mean anything to you, But what it signifies is the large L, the luminescence, is a calculated value of the XYZ coordinates for a particular light location or flash location, and it in red, green, and blue. What is the value? What is the luminescence or the light value for each one of those at a particular location? So with the three of those, it comes out to nine different values for each one of the light sources. And it is and that's basically the math behind it. Now, this wasn't something that we did over a cocktail dinner napkin. This is something that actually was presented by Tom Malzbender from Hewlett-Packard Research Laboratories in Palo Alto, California. They have a cool job. If you ever want a job that's just a think tank, all they do is sit around and they write mathematical equations, and they try to apply these things to real-world situations. What ifs? What if we wanted to kind of get a three-dimensional image of something? How would we build that? And in his particular case, he was looking at video gaming. How can we get a more realistic figure or movement in the people in video gaming? You know, because video gaming is a very big industry. But they really don't look at it. The researchers over at Hewlett-Packard Laboratories, they aren't constrained by anything. All they have to do is think of things, and they just kind of play with kites and do a lot of different weird stuff, whatever they want to do, as long as they put out some product. And it really doesn't have to be something that's applied directly to computers or something else. Although, for the most part, most of what they do has a direct application to computers. In this particular case, they were looking at this polynomial, and Tom Malzbender and Dan Gleb over there, they came up with this idea. And the idea was to bring three-dimensional images, or images out of a two-dimensional thing. They gave a presentation at CAC, I believe.
Yeah, it was a California Association of Criminalists dinner.
One of my criminalists back in the laboratory came back and said, hey, this is kind of a cool idea. And at that time, one of our mandates was to kind of bring some technology and look at kind of cutting-edge technology. So I kind of grabbed onto this and looked at it and said, hey, for the application of forensic science, this probably has a lot of applications. So James and I met with Tom Malzbender. We went over to Palo Alto and spent 2 days with them, and they gave us a demonstration off of their dome, and we would look through several of the applications that might be possible for us. And from that, this project. It really worked out well because the NIJ solicitation came out after that. We were going to do it regardless, but as long as the feds were paying for it, it was great. And it gave us some neat equipment, and it allowed us to look at various things within the project, such as digital cameras and different things that would help us set some type of policy on looking at images themselves. So, in looking at it, this polynomial is simply more than looking at the light vectors at a particular location and then all of the locations. Imagine if you knew the value here between this light and this light, and you know you have a fixed object. The camera sits on top, you have a fixed object on the bottom, you have a light source over here, and then you have a light source over here. All it is vector analysis, and you can calculate the value in between there to infinitum. And that's what really works for this particular thing. And we'll compare and contrast this a little later to other types of things like bump mapping. I'm sure you guys have looked at bump mapping, and some of your instruments probably have some bump mapping in looking at things like SEMs will have it for looking at various types of elements. They color different types of elements on there, or on the FTIR going over a different surface to do bump mapping. Bump mapping is kind of a crude transition into this PTM. PTM actually gives you a lot smoother application to bump mapping. Okay, so as I said, Tom Malzbender has created it. And the first applications really were archaeology and paleontology. You saw the tablet that I put up there, and they looked at a lot of different things. And imagine these giant domes that they had to use for archaeology, and they're pretty large. They're pretty huge in trying to map out walls and look at the hieroglyphics and a lot of those different things. But it required a very large dome in order to do that. The art world has a lot of interesting applications to it. At the Louvre, what they're doing is they're using kind of a portable modification of what we design in mapping old master paintings. And by looking at every angle of it, you can capture every brush stroke. So if anyone was ever trying to forge one of these things, you could tell right away. I mean, the brush stroke, every brush stroke is captured forever. So if there was ever a question of it later, they'd bring up the image and boom, boom, boom. You could tell right off the bat whether or not it was or not. And the interesting thing is when they looked at that, there was one painting of, I think it was a Monet painting, that in the background you can see where they started painting a sailboat. Monet started painting a sailboat, and then he wiped it out and then went on to another painting. But you know, because of the shallow relief angle, you can see all of a sudden in the middle of this painting comes a sailboat, which is pretty cool. No one's ever seen it before. And all of a sudden now, with this technology, you're able to see those kind of things. So what you really see with your eye sometimes isn't all that's there. It really brings out a lot of different applications. Henso in forensics, really we only concentrated on footwear and tire impressions. In question documents, there would be a huge application, as would there be in latent prints. I think because those are kind of impression evidence, you should have no problem in looking at these things and documenting and being able to get more detail than you ever have before. And as you saw with the second derivative, you should be able to even bring up more detail than you would have saw just in a traditional image. So, I mean, really the sky's the limit on these things. On these trilobites, there are different types of modes that we're looking at in here. And in the different modes, you can see in image 1, where it's just a straight-on shot. On 2, it's an oblique virtual light and an inverted image. Number 3 is the specular enhancement. So what this looked like in number 2 kind of looks like a depression. Now in the specular enhancement, it almost looks like that depression has been raised up above the surface, which allows you to see even more detail. And then the addition of the overlaying of images 2 and 3 is in 4. So in each one of them, and you know, it's great because then you have the ability to look at more different types of detail than you ever would have before. Okay, so if we look at a surface normal, or that is a straight-on light shot to the this tablet, and then you look at the specular enhancement part of it below it, I mean, clearly you can see some pretty good detail. And that detail is, you know, for at least archaeologists, is the cat's meow or whatever, you know. I think it brings out much more detail than you ever would have imagined before. And so this application really kind of opens up a wide variety of different things. And in seeds, this illustration is really, we have this interactively that I believe James is going to show you later, but it allows you to bring up more detail even in individual seeds. We can go down and look at individually these seeds and then look at the various ridges within a seed. So it brings up much more detail than you ever could have before. And then depth of field studies. And this comes in these video games too. You're looking at various things in a depth of field. And so this is the original on the left, the purple image. That is the original dome that was created. That was made out of sticks. And you know, all you're talking about is a geodesic dome. That's all it is. And then on the right is, actually that's Hewlett-Packard's dome because it's black. Ours is white. Okay. But the inside surface has to be black. You're looking for reducing the reflectance in there. But they used a black plastic. We used a white because that's what was available.
Well, clear plastic, white primer on the inside, and then black.
So what we have here is all of those little green circuit boards, your local Radio Shack, flash strobes. That's all they are. And they're run in a sequence, and that sequence kind of is, you know, you tell the computer which one to fire in which sequence. Okay, and this is our dome with a camera attached to it. We built this particular dome, and it has 64 different flashes on it. Okay, so let's see how much time we have. Oh, I ran through that fairly fast. What I'm going to do next is to show you a PowerPoint presentation. Some of the images you'll see are things that you saw in these because I stole them from Hewlett-Packard. But this one was done by Tom Malsbender, which he sent me last week, and he thought there was some pretty cool stuff in here that you guys would enjoy. So the difference between texture mapping and bump mapping, there are pros and cons of each. With the bump mapping, you have a light variation, whereas the photographic input, simplicity, and hardware support are part of the texture mapping. The con is you have unrealistic silhouettes on texture mapping and static light. So has anyone seen, do you know what I'm talking about in bump mapping? It looks very stick-like. It doesn't have a very good smooth transition from image to image or from side to side. And so when we look at this thing in things like leaves, you could almost feel the leaves either depressing or coming out of the image towards you. Oh, can you, let's see that. I'm sorry.
Oh, wrong ones. That one? All right.
Okay, so this is just that one, and then we have this, yada, yada, yada. Okay, so as I was talking about earlier, if you think about this thing, each color, the red, green, blue, is represented by each one of those layers. And you can look at the various, U and V are defined as the coordinates in space. So you have to know what the coordinates are in space, and you know it should be fairly easy math from there. But there's an easier way of doing it, and we'll talk about that also. So what we have is this kind of pixel color changes and this kind of this mathematical formula which allows for a sum of everything at a particular location and the sum of all of those locations together and being able to calculate a total light value across the entire hemisphere. And all of these things, these PowerPoint presentations, if you want any of them, I think what we're going to do is we're going to put them on the laptops in the computer room, and you can just copy them to your thumb drives. How's that? So you have the visual things. Okay, so in looking at this thing, we're looking at the RGB is defined by the red, green, blue areas, and then each one of those LR primes and the LG prime and the LB prime are the luminescence values, the chrominance or the luminescence values at each one of those places. So what it does is it allows you to kind of pack all that in and then turn on, turn off, vary each one of those values. Okay, so as in vector analysis, you have a static, which is the camera on top. You have a static image on the bottom, and you know the angle. If you know the angle of the light, you can calculate all those things, and then you can calculate the distance between the two values here. Between those two values, you can calculate the luminescence of any space between the two, which is kind of cool. It allows you to go on with looking at an infinite number of angles. No longer are you stuck with 4, or 6, depending on how many photographs you take for shoe impressions or tire tracks or anything. You're not limited to those anymore. You're limited to everything in a sphere, anything within that hemisphere, which is kind of cool, because that's where the detail is going to be in making an identification, or being able to say more about an image than you ever could before. So in another kind of display of what we're talking about is the red, green, blue is all combined together, and those values are placed into the L, which is the top image up here. So these are all kind of a combined in here. I feel like John Madden. Great. Telestrator. And then the ENC down the bottom there is nothing more than encoding. It is a kind of a language very similar to JPEG. It's a compression of the files. We currently are using JPEG files, which is a compression. And we looked at some of the detail to see how much detail we are going to lose by compressing the files. And truthfully, we don't really see that much. We used an Evans scientific chart for resolution in trying to determine how much we're going to lose in that compression. We really haven't seen that much if the camera is high enough resolution or megapixels, right?
Yeah.
So, and James will talk about that. So, when we're looking at, we're trying to bring more of a three-dimensional image to two-dimensional applications, and being able to bring out more relief, more detail. And really, that's what it is in impression evidence, is how much detail can we capture? How much detail is there to be able to make a comparison? And in this case, you can see the difference even between the top and the bottom. There's a lot more detail that you can to be had, and especially if you were going to be doing. Think of this as the bottom of a shoe, a shoe sole, and an impression. Think of the difference between the top and the bottom. There's a night and day difference, and this is what it allows you to do. Not only that, but because it's all a computer-controlled system, it allows you to take all those things, collate them within minutes. So you can have a PTM file within probably 5 minutes, 7 minutes, which is great, compared to, holding that camera out there, taking the pictures, printing the images, and then trying to do your comparisons. I mean, think of all that time it takes you to do that. And if there's a lot of detail in there, you're probably going to take a lot more images around to shoot. Think of all that time it takes you to do all of that, then print all those images, and then be able to go one by one and look at each one of those to see if you captured the detail you needed to compare it to that shoe. Now all you have is a roller ball, man. This is all like video games. It's right off the computer. It allows you to capture that image. And that's one of the things that we thought about later, that may be a future research project, and that is to be able to put them side by side. Be able to capture them and to have two polynomial images all at the same time, and then to be able to move them around. on the image so you can look at these things side by side, which would be great. And the computers, I believe, are fast enough now. There's just not an application out there that does that. There is Mideo does have a side-by-side images to images, but they're static images. They're not interactive images. So that's a little different, but that would be something that would be really cool if you could put the reference shoe on one side and the image on the other and just do a straight side-by-side comparison. I would ask for a 42-inch TV, to tell you the truth. High D, you know, and that way you could sit on the wall, look at it, and it would be real cool. I mean, you'd feel like CSI. Hell, they got it. Why can't we? But that is where I think the next step is going to be, the comparison. Once we captured it, being able to get better images, now it's up to the point where do we have the ability to do a side-by-side comparison quickly, easily, and those things. Yes?
Just a question. I use dual monitors for doing comparisons, and couldn't you just open the application twice in two windows and do one on one side and one on the other?
Yeah, you can do that. You're flipping back and forth.
Yeah.
You have controls. If you remember, you had a gray side and then the image side. So your controls are on that one side. If you got it small enough that you could keep those control boxes open, yeah, that would work. But by the time you get them on a normal size monitor, they're pretty tiny. The images themselves get pretty tiny when you start squashing them side by side like that. And if you start overlapping them, then you're going to have to keep flipping back and forth to get to your control. And then once you hit that window, then the control panel pops over to the image side of the other one. So yeah, you can do it. I've found it kind of cumbersome to try and do it that way.
Dual 22-inch monitor.
If you have two separate monitors side by side, yeah, there you go.
Yeah, I think that would work. But I think the other thing that you should look at is to be able to put it all on one screen. Maybe that's your justification for a 42-inch screen. You know, and you split the screen in half, and to be able to put lines and stuff in there, or circles, and be able to really trying to capture all the different detail that you're really looking at to be able to do it. Now, you can do some of that in Photoshop on a static image, but not on the interactive image.
The other problem, you know, if you got two of them open, you've got to try and match your light positions. Remember on that hemisphere? So you're going to have to go to one and go, okay, I'm about here, and then you're going to have to try and match that over here because you want the images to look the same. If we could get two of them side by side with a single control where those light positions are going to move at the same time, that's really going to be the best way to do it. Both at the
same time, you know you're looking at exactly the same angle with each one of them.
Do you have a way of determining what your light angle is? You know, like if you're mapping a sperm slide, you could hit the coordinates or something. Can you hit a button and record which light image you're using?
No.
Yeah.
That's a short answer.
Yeah, you can tell the direction just by the shading on there, but the exact coordinates, no, it doesn't. That's all done in the background in the mathematics.
Basically, the 64 pictures that are taken, those 64 flashes, we know the location of each of those flashes. Using that information, the FITR program, when it creates its PTM, it's actually a separate entity. That PTM file is a separate file, and it's a model of the light space. So there aren't any actual coordinates in it, because the whole thing is a model based on those 64 images. So you could probably guesstimate where I'm at on that hemisphere and then go back to your model and figure out what photo or what image you're close to and probably guesstimate an area. But there's no way, it doesn't just pull up like, okay, I'm at XYZ coordinate this. So there's just no way to do that.
Your mouse pad goes in XY once you put it into a 2D screen.
But remember, when you have 64 flashes, those things all get merged into one, and every value is calculated in between those things. Those 64 light positions all kind of disappear. All it is that we're saying any place on that hemisphere can give you a different angle. And so that 1 through 64 no longer holds because it merges it into that polynomial. And now the calculation between all of them, it's so infinite that you couldn't give it a number for any one of them. I mean, unless you kind of wrote in the program this, you know, kind of used the north, south, east, west kind of thing. The 64 light thing just kind of disappears. Because it's all merged into this model. It's a light model now. It isn't 64 individual images anymore. It is a merging of all those things and a calculation of the luminescence between every one of those points. Does that make sense? Yes.
Maybe I'm jumping ahead here, but you're talking about doing the comparison work in this.
Mm-hmm.
From your crime scene image to your shoe,
Right.
you've got the, if you're trying to get it exact, you've got that orientation situation where you may not ever have it exactly the same anyway. So, is that an issue? I mean, have you looked at that as far as?
Well, once you have the shoe, we use test impressions. I mean, if you have the shoe, we're making a test impression and comparing that test impression to the screen. Does that make sense? It's not a PTM image of the shoe.
So you're doing a three-dimensional impression?
The scene impression is going to be the PTM. And you've got a shoe, we're going to make a test impression, and look for the defects and compare those defects to the image at the scene. So we're not making a PTM of the shoe.
I guess my question would be, why not?
You could do it. You could flip it. You're looking at the shoe. You'd have to invert it. There's that problem, which you'd have to use Photoshop first. Okay. But part of the thing is all the images have to be identical. You have to do the same thing to every image. Okay. So this PTM file, you can't go in and just invert the image on the PTM file. You have to go back to your 64 images. You'd have to invert all 64 of them identically, then make another PTM from those images. So
although you can make a PTM from the test of the shoe, and that should give you that. Because we're not always sure whether or not some of the defects, cuts, marks in a shoe actually translate into when you make an impression. So, I mean, I guess maybe we're just old-fashioned. We make test impressions. But that test impression could be made into a PTM file.
Yeah, you could certainly make a soil test impression and then capture a PTM of that and do an on-screen side-by-side.
It just depends on the matrix that it's on. We try to emulate, at least we do, in the different types of surfaces that may have caused a shoe, whether or not it's a negative or positive impression. And that way we're more assured of the type of marks that we're going to or may not see from the bottom of that shoe. Yes?
You said the mathematics in this allowed you almost an infinite variation in the apparent positioning of that light, so an exact alignment wouldn't really present much of a problem, would it? Because with the mathematics, you can put that light any place you need to, can't you?
Yes. Well, there's two issues here, whether or not you're opening two PTM files and to be able to get exactly the same light location is, because you have an infinite number of them, it's pretty tough. But if you open one PTM file and being able to use two images, you're right, the orientation of each one of those would have to be exactly the same to be able to do that. You see what I'm saying?
If you have two PTM images that you're comparing from two different items, the mathematics would allow you to place that apparent illumination any place within that sphere that you have, right?
Mm-hmm. It's pretty much like you're standing at the scene with a flashlight and you're just moving it. So you can move that flashlight wherever you want and highlight the detail. I'm sure everybody's here done footwear impressions. You get that one photo that highlights the toe, really well, but the heel's dark. And you get one that highlights the heel, but not the toe. Well, in this way, you can really bring it across in real time and say, oh, okay, well, now I've got the middle of the soles highlighted really well. I can move it over here and highlight, this texture going the other way. Now I can get light going across it. And that's really the biggest value, is you can always find the perfect lighting. But maybe I'm misunderstanding. You're talking about replicating it?
The optimum lighting for your viewing, you may or may not have one of those little flashes in exactly the right location.
Yes.
But the mathematics allow you to give an apparent illumination from that optimum point.
Yes.
Exactly what you're saying. Yes.
Yeah, because that's a model. There is light from the entire hemisphere,
Right.
yes. You can select exactly what lighting position you want within the PTM program, because that's a separate file. You still have those 64 images saved separately. So you're always going to have the original 64 data points, if you will. But then that model hemisphere, lighting hemisphere, yeah, you can pick exactly where you want the light to be.
Yes.
Light mark situation, would it matter if you used a negative model or a positive model, one, and then the ones embossed, and use this?
No, it really doesn't matter either way. Remember, though, the angle at which the flash is really depends on whether or not it's raised or lowered. So on a depression, you would have, you would need a higher angle, because if you came in low, you might be able to see more image on one side, but it would shade the other side. And so you would look more at a topical level. If it were more shallow, like traditionally shoe impressions aren't that deep, and so the shallower angles tend to give you more relief or better image control.
But again, once you have a PTM of it, you can pick whatever angle you want.
Right.
They're all there.
Because remember, we're mapping from the very lowest one, which may be dark in some cases, all the way up to the top, where the top of the dome is. Okay, so this is kind of a illustration of the particular image. If the blue part here is the image, and we have the camera's always fixed wherever it is. And if you know the exact positions of each one of the flashes, all you're doing is calculating that. And then you calculate each one of the light values between there, like that. So, I mean, it's fairly simple math, because it's just measuring the light values at two different locations, and then being able to calculate each one of those values across there. What is the difference? What is the luminescence between the two? So the application is fairly straightforward. It's something that you probably learned in physics or in math classes anyways. But it's a real world application to that. And yes?
Is the dome portable for crime scene work?
To get to the heart of the matter. We have two domes here. We have a one that we call our laboratory dome, or in the lab you saw the big dome thing. That really kind of doesn't lend itself to going out into the field. And then we have one that we came up with that's kind of like a half arc, and that's for the field. Although it's a little big right now, the reviewers of our paper were critical of the size of it. And so what we're doing right now, our latest research, what we're doing right now is looking at LED lights rather than strobe flashlight. We're using, for our portable, we're using slave flashes, battery-powered slave flashes. But we're looking at using LEDs to shrink that 3 foot, because we wanted a distance between where the image is and about 3 foot out, so that thing became big. So when we're looking at LED lights, we can control the distance a little better, and we're trying to reduce it down to about 2 feet, 18 inches to 2 feet. And we want a smaller portable, carry it. And as we reduce the size, this one is built out of aluminum, hollow, just tube aluminum. And as you get smaller, and with LED lights, you can go to plastic, which is cool. It's just like China. Make these plastic molds, and that would be much easier, much more convenient, and much lighter, portable. And we're looking at a true portable system. Now, there may be some concern as to doing it in the daytime. Not all crime scenes happen at night, but they always seem to happen at midnight or 2 in the morning. But those that are in the light in the daytime, it's no different than what you do on your flashes right now. What do? I know what we do. We use a black cloth. We have a trout. He stands there, and he blocks the sunlight, depending on the angle. That's all they do, and that's all you need to do on this one, too. And the portable unit itself, although we thought about doing it motorized, we didn't have enough money, truthfully. But it can be motorized to stop at 8. The portable we have right now has 8 flashes on it. So we have a kind of a protractor and 8 different stops on it. So it stops here, and the way the program's written, after it flashes 8 times in that series, it stops. You put it in the next position, hit the go button, it's 8, and it's manual. Now you can use a motorized stepper motor to do that, and that would be cool. That would be much simpler. That would be really hands-off at that point. The whole thing is run. The flashes currently are run off battery, as I said, but the system is run off the laptop, so it is portable. You don't need to plug it into an AC outlet or anything else. It's all USB cord. USB is great. It just allows you a lot more flexibility than we had before. So yeah, you can bring it out to the field, set it down. The current version we have right now has leveling feet on the bottom to accommodate some of the uneven surface, and it has a mount on top for the camera. So it is truly portable.
It's just kind of big right now.
Yeah, it is a little big, you know, but it is what it is, and it's the first cut of it. But the LED lights, the current versions are going to be LED lights, and it should be much smaller. And I think if we can get it into much smaller and into plastic, it would be much cheaper too. So.
Yeah, I'll talk about this when I talk about building your own dome. One of the things, it's basic flash photography. You know, the brightness of your flash determines how far away that flash needs to be. So, and that determines the radius of your dome, which really determines the overall size. So the brighter your flash, the further away it's got to be, the bigger the arc, the bigger the dome. So we need to basically get a flash that we can step down, that's not going to be very bright, so we can get it close to the object to keep the radius of that dome fairly small. So LEDs, I think, is going to be the way to go to keep things down in size. And basically the portable one we had, the flashes that were available to us, the digital slave flashes, the distance that was required to just get a good image without, you know, whiting it out or being too dark, really determined the physical overall size of it on this first go-around.
And there was, you know, the LED technology, even within the last 3 years, it's leaps and bounds of what it used to be. I mean, imagine even your cell phones probably have a little camera with a flash in it now. Those are the LED lights that we're kind of looking at, the ones that are used in cell phones, to be able to control the amount of light in there so we can get closer to the object and not wash it out. So it's kind of a challenge in measuring using a light meter how far away we can get with different light sources, and then, you know, trying to reduce that size. I mean, we'll never get it to putting in your back pocket, but we'll get it to a size where it would be easily portable. Okay, so we looked at some of the cuneiform tablets in the various aspects. This is a Ushabti statue. And so, you know, it looks at, in diffuse gain, it looks at, you can increase or decrease the second derivative. So you can go from anything on the left-hand side all the way to where it almost looks like specular enhancement on the right-hand side in diffuse gain. So, you know, as we talk about this, you'll be able to interactively not only get your hands wet and try it and play with it. James will run through various aspects of this as he presents along too, and you'll be able to see that, you know, you'll be up and running in 5 minutes. I mean, it isn't rocket science. It isn't something, if you can use a mouse, you're in. You can do it. Okay, so we're looking at, oh boy, that's not a good picture. So this is various applications in here. This is a forensic application that I was talking about earlier. This is either 10 or 15 pages, I can't remember which, below. And the FBI went to the HP research laboratories to ask for their help on this particular thing. I mean, that many pages down from the original writing is pretty impressive. And they were able to write the whole document, the whole page out, which was impressive. So, I mean, you know, in question documents, now you can see different applications. Imagine on latent prints, you should be able to even have more images on there and more detail, which is great. And for latent prints, I mean, you could even use a small little dome. In fact, the one that James was talking about, we had a student intern from New York, and that's what he did his master's project on, is mapping that cartridge case, and he used a salad bowl. So if you have a salad bowl at home, drill some holes, you're in.
Yeah, he just used some small LED lights and just, they were plastic salad bowls, so he just cut holes through them and just stuck them in positions. And he just had simple on-off toggle switches for each of the lights. So you turn one on, take a picture, turn it off, turn two on, take a picture, turn it off, turn three on. Just keep doing that. And I think the radius he used was about 8 inches because they're very low voltage LEDs. So, you know, again, you can design something to fit almost any application you want. It's just a matter of getting the right light out.
When we said the minimum is 50, that's for a 3-foot dome. As you shrink it down to 6, 8 inches, you don't need that many lights. I mean, now you're reducing the size of that thing. You don't want them right next to each other squeezing because, I mean, you defeat the purpose of being able to use the mathematics behind it. So in a smaller dome, if you're going to use it for mapping out teeth or bite marks or something else, once you've reduced that thing down and you're in, you don't really have to put that much work into it in designing that thing. You know, in any hemisphere, as long as it's fairly symmetrical, will do. Salad bowl is symmetrical.
Yeah, he actually reduced it down to 32 when he did that, and the images look good. So.
Okay, and this is the Louvre, and as you can see, this has some pretty big flashes on it. As you can see, the imaging of it, the light arm here, they used our kind of half-arc dome, and they applied it to something that they don't really want to take these pictures off the wall. And imagine some of the pictures are pretty big. And they mapped a lot of the images in the Louvre, and I would imagine a lot of different art galleries are going towards that to defeat some of the forgeries and those things, and to map out every brushstroke in a painting. Okay, so this is pretty cool. This is the latest thing that Hewlett-Packard Laboratories has been working on, and this is called real-time enhancement. This is pretty cool. You have to have a faster camera, and you have to have a big graphics accelerator card. So if you ask for that gaming computer at work, you probably get it doing this. It allows for that big graphics. It's a fast transfer of the data. The data has to be able to be transferred very fast, and it's almost like a video picture. It comes through as almost like a video. That's the real-time kind of enhancement. It allows you to do it, and it looks almost like a three-dimensional rendering or a video of the picture now. And that's really cool. I think, you know, moving towards that, and as you can see on this one, they're using LED lights to capture that, which is kind of cool. Actually, that is a different application on there. If you think about all those spider webs on that particular spine, that's just a different way of creating that dome, that hemisphere. If you look at that thing, I mean, all it is a ring around the camera, and they position the lights in different places. This is pretty cool. Now that truly would be portable. That would be very portable. But the distance you need to a shoe impression, I'm not sure that camera is, it looks like it's a little close. So, in looking at these various things, there are so many different applications and ability to do it. It's anything from, you know, the archaeology, as we talked about. Procter & Gamble has built one of these to look at tablets and quality control. You know, be able to map out where some of the imperfections are, to look at their tooling and their equipment. This is a geology, this one is pretty cool because they don't map out the XYZ coordinates. What they use is right up, where's my telestrator? I just love this thing. This thing here is a cue ball, is a round ball, and they put it right in the same place on an image. As you can see right here, that is the cue ball. So you have your assistant, I call them trouts, standing right there, same place. And what happens is that you're able to calculate the position of each one of the flashes based on the light as it hits that sphere. So you know what a sphere does is if it's in the same place and your camera's exactly at the same place, the only thing that varies is the flash. And that flash sends the brightest spot of light in the angle at which that is. And if you know that angle of the camera, you can calculate all that out. And that's pretty cool. It's very, very, very easy. And that way you don't have to kind of create the whole dome or anything else. You know it, which is kind of cool. And that's one of the things that you could do in a field is capture all those images and then calculate the angles back in the laboratory and then merge all those files together. So that's just a different way of doing it. It's more labor intensive. When we looked at this, we were looking more towards what is the easiest way of getting this done without having to do a lot of those calculations. Okay, so in conclusion, I would say that if you go to hpl.hp.com/PTM, there are more articles than you ever want to know about on there, and there are different applications, and the PTM viewer software and everything is there, although you have them on your thumb drives. So all of that stuff is, for the viewer, and those things are all on your thumb drives. And I believe, is the stuff for calculating out the XYZ coordinates of each one of the lights on there too?
No, I didn't put the Excel spreadsheet on there.
Okay.
I'll go over it.
Okay.
It's a pretty simple
Okay.
process.
So the PTM Fitter program is one that you can ask James and he'll give you a copy, right? But
Yeah.
you're going to have to calculate it out for your own anyways.
Yeah, and there is a user license agreement is in there as well. It's basically when you download it from Hewlett-Packard's website. It's free to download, but it's this thing, I will not use this for making money for myself kind of thing. It's really, they've released it for academic pursuits. So as long as you're using it in the lab, things like that, they don't have any issue. Yeah. But I went ahead and included the license agreement on there. We'll talk about the software. There's really two parts to it. There's the Fitter program and then the viewer program. And the Fitter program is what makes the PTM file. The viewer program is what allows you to see it.